What inspires me about science is to understand how the world works and the laws that govern nature. I am Chaim Garfinkel, a professor in the Earth Science Institute at Hebrew University. I focus on atmospheric dynamics and climate variability with a particular focus on subseasonal to seasonal variability and predictability. Weather forecasts are very reliable on short timescales, let's say up to 5 days or so, but beyond that, their reliability decreases dramatically. And most current forecasts are almost useless on these longer timescales. So my research aims to extend the duration of reliable weather forecasts to understand the processes that are important for these longer timescales. Weather and climate models do a good job at many things, including an impressive ability to reproduce Earth's current climate. Nonetheless, they struggle with some things. Among these is the difficulties in predicting the dramatic warming of the pole around 20 kilometers above the surface. This variability is linked to extreme rain and drought in regions as diverse as Scandinavia, Spain, and Australia. Understanding why these links exist and focusing on what models do well and what they struggle with allows for better early warnings. We are still researching how climate change will affect these kinds of dramatic warmings. Predicting this with longer lead times will allow for more effective adaptation and better planning. My reaction when I heard I received the prize was a mix of surprise, excitement, and happiness for the recognition. I am humbled to receive the Blavatnik Prize, and I'm excited to join this exciting community. Every year, tens of billions of dollars of damage is caused by extreme weather. My dream is to be able to issue bias-corrected forecasts in near real time for more reliable predictions that can help save lives. Thank you for the wonderful video. It's my first time seeing it, so it was really cool. So good morning. My name is Chaim Garfinkel. I'm an honor to be part of this event, and thanks to everyone for coming. And that's my 2-year-old back there too. So Earth's climate is changing, and we're causing it. Temperatures have warmed over the past 150 years by over a degree, and over the past 40 years, most of that increase has been over the past 40 years. What's less clear is how this warming impacts regional climate and on timescales that actually matter for planning and for adaptation. And that's what my research is about, is understanding the impacts of climate change on shorter timescales and in specific regions. So climate extremes such as heat waves, floods, droughts, and also severe cold in some regions is actually increasing. And with devastating consequences on industry, on people, and on utilities, transportation, and so on. And so we are interested in understanding these impacts and predicting them, understand what the role of internal variability and on top of climate change. So I'll give an example of what we call a forecast bust. Despite decades of investment in climate models and computer models that predict Earth's climate, predictions of extreme events are still not reliable. I'll give an example. This is a forecast that was issued in 2012 for February 2012, and showing warm conditions in Europe. This is what actually happened. In this case, the blue indicates cold, the red indicates warm. And so temperatures were enormously cold over much of Europe. There was actually snow in Rome here, ice in the canals of Venice. About 650 people died in Europe and during this cold event. And the ambition of my research is to understand these kinds of events and why do models sometimes fail. In this case, it was a pretty drastic failure, and to improve the reliability of these forecasts, understand why they fail sometimes and when they're reliable. And so there's two main aspects of how we do this. The first is to analyze output from currently existing models and to understand the systematic errors, which of the models do well, which of the models do poorly. And the second is to better understand the underlying physical processes that govern atmospheric motion, dynamical motion in the atmosphere, storms, heat waves, cold snaps, and try to improve the representation of these underlying physical processes in models and climate models. And so I'll give an example, this time on decadal timescales. This is what temperature anomalies look like in this 11 to 12-year period, 1986 to 1997. Temperatures were warm in Eurasia and cold in Greenland, eastern Canada, and also cold over us in the Middle East here. And the question is, so this is what actually occurred in reality. If you look at models, you get white, essentially nothing. And this is just taking models at face value. And so somehow we spend, billions of dollars on developing climate models and weather models, and they're useful in sometimes and less useful in other times. And we want to extract as much information as possible from these models, and we need to extract these predictable signals. And so how do we do that? So there are specific processes in the atmosphere and also the ocean that allow for predictability on timescales from the subseasonal to the seasonal to the decadal. And so a really big part of my research is to understand these physical processes. So for example, one key process involves the tropics, the tropical convection. We have a series of phenomena in the tropical atmosphere and the ocean, one of which is the Madden-Julian oscillation, which is basically an envelope of deep convection of essentially lots of rain in a particular region and less rain in other regions in the tropics, and this tends to propagate eastwards from the Indian Ocean into the Pacific Ocean. And in addition to that, besides Madden-Julian oscillation, there's also El Nino Southern oscillation, which is another phenomena in the tropical atmosphere and ocean, where temperatures in the Pacific Ocean warm or cool on a timescale of 2 to 7 years, and this also has impacts on where there's more rain or less rain in the tropical atmosphere, and that both the Madden-Julian oscillation and the El Nino Southern oscillation can launch waves. Just like a spring you string on a guitar, it launches a wave. So too in the atmosphere as well. If there's anomalous rainfall or a big pulse of rain in the tropical atmosphere, that can launch a wave that propagates in all directions and into the mid-latitudes as well, into the polar regions, and affect our weather. In addition to that, a big part of my research group is focused on interactions between the lower part of the atmosphere and the upper parts of the atmosphere. So, for example, you can imagine the layer of the atmosphere from 10 kilometers to 50 kilometers above the surface, which is known as the stratosphere. Waves can propagate upwards and both downwards. And it turns out the stratosphere is more predictable than the troposphere. And because the stratosphere is more predictable than the troposphere, this region up here is more predictable than what goes down here. If you can understand what's going on here, you can actually predict weather on monthly timescales, even seasonal timescales. Besides that, there's also phenomena in the tropical stratosphere, from about 18 kilometers above the surface to about 40 kilometers above the surface in the deep tropics. Winds alternate between westerly and easterly direction. And when we have westerly versus easterly winds, that changes actually the intensity of rainfall in the tropics. It also influences wind patterns in mid-latitudes in the subtropical regions. It also impacts wave propagation in the whole atmosphere. And so there's a series of processes that in my research group, in terms of the daily what we actually do is we focus on these kinds of processes and understand where they come from, why they exist, how do they impact surface climate, and how do models represent these processes. And are models systematically biased? And in many cases, they actually are systematically biased. For example, we have research that indicates that this wave train from the tropics to mid-latitudes is actually too weak in many climate models, which leads to a lack of predictability. And so the goal is to fix this, is to understand the processes, and then in models we try to fix these things and or somehow post-process the data to give us reliable predictions. And so I'll give one specific example involving the sudden warming, involving the stratosphere here. So I'll just give one specific focus here involving the stratosphere. So I'm showing here temperatures on the 13th of January, 2009. Temperatures on 13th of January, 2009 were pretty normal for this region, 30 kilometers above the surface, minus 70, minus 80 degrees. That's pretty typical this time of year. This is 11 days later. This is the 24th of January. 11 days later, temperatures have warmed by over 70 degrees at 30 kilometers above the surface. Temperatures are actually above freezing in Greenland in late January. This event is known as a stratospheric sudden warming event. And when this happens, this has a big impact on surface climate. And in particular, this particular event in 2009 was followed by snow in London, and also a range of impacts in Eastern Europe, in Europe and also Eastern US. And so this snow was actually predicted 5 days in advance. However, we can actually try to predict these kinds of events more than 5 days in advance, even a month in advance, if we can actually predict the conditions in the stratosphere. And so it turns out that some models systematically fail to generate these kinds of warming events. There are some models that actually you can run the model for 1,000 years, you'll have like maybe 2 or 3 events, and in reality, these happen 6 times a decade. And so it turns out the models that do a poorer job with these processes have less reliable climate projections in the eastern US and Europe. And so it's actually really important, not just for weather timescales, but also climate change timescales, to get these events right if you actually want to know what will happen in a given region over the next century. And so another stratospheric sun warming event occurred in 2021. This one was actually followed by devastating impacts in the US and central US and Texas. There was $200 billion in damage and losses in Texas associated with this event. Basically, the entire energy grid in Texas went out for almost a week, parts of it for almost a week. And so this cold snap in Texas was followed a sudden warming in the stratosphere, and we actually had a paper that in Science on its front cover about this event, trying to understand the connection to the stratosphere and basically involving wave reflection from the stratosphere down to the surface that actually led to this event. We also talked about how models represent these kinds of events or lack thereof, how they actually do a pretty bad job of representing this kind of event and what we can do about that and how we can fix that going forward. So just to recap, the goal is to have better models now. So using the models that we already have, I showed these 2 panels earlier. We had the observed temperature anomalies in this 12-year period. We had warm here, cold here. The models, if you just take at face value, essentially we're just white. There's no signal whatsoever. If you can then do some post facto bias correction. You can sort of play with the models and try to extract the signal, and you actually can do that. So there is a signal in the models, but you have to essentially do post facto bias correction to get that signal out. And we want to be able to do this in near real time, essentially, given the models that are coming out. Can we actually predict weather going forward and from time scales from the subseasonal to the decadal? And we also want to understand the processes that underlie this predictability, whether it's from the tropics, whether it's from the stratosphere, whether it's from the QBO, understand where this comes from. And these 2 aims reinforce each other. Basically, together we can transform how we predict and understand climate. And I'm really excited about not only the basic science and the core science, but also the practical impact. And so these improved projections are important for a whole range of industries: agriculture, travel, transportation, utilities. They can save every year tens of hundreds of billions of dollars in damages associated with extreme weather, and to the extent that we can predict these kinds of events better, we can mitigate those damages. And so, yeah, I just want to close by thanking everyone. So my group, thanks everyone for coming, of my group. Good to see everyone here. So I guess taking advantage of the people nearby. And yeah, so I want to thank my group and also the few members of my group who are not here today, but also my collaborators over the years, and both in Israel and also internationally. I want to thank my family, and thanks Sarah and Grandpa for coming. And Grandma as well. Thank you for coming as well. And my kids who are in school right now. And I want to thank the New York Academy of Sciences, the Blavatnik Family Foundation, and Bavotnik for this amazing event, and also the Israeli Academy of Sciences and Humanities. I'm closed by thanking everyone here for coming, and I also want to mention the Kochat Bitachon for keeping us safe and allowing us to have this event. That's it. Thank you. גם בעברית, גם באנגלית, מה שנוח. אפשר לשאול.
This rapid warming you described in the earlier presentation, in the 30 kilometers above sea level.
Yeah.
Is it related to global warming? How often it happens, or is it just kind of not how?
So, is it related to global warming? So, if we look at the frequency of these events let's say we take 30 different climate models that exist, and look at some models predict these kinds of events will become more frequent. Other models predict they'll become less frequent. We still don't really understand why. We actually are working on that. I mean, David back there, one of the things we're looking at is actually understanding force changes in the stratosphere, where those force changes come from. Certainly it matters for the surface. I mean, models that predict more of these kinds of events, the impact of climate change in Europe and the US is very different than models that have actually fewer of these events. We understand part of the physical processes that would indicate whether there should be more or fewer of these events, but then when you have a complex model with lots of different things changing, I mean, half the models give you one sign, give one answer, the other half give the other answer, and we still don't really understand why.
And let's say just in the last century, do they happen more often or less?
So as far as we can tell, it's been flat. So over the past historical record, it's been pretty flat. There's decadal variability. So for example, in the 90s, I mean, a big part of what happened in the 90s and the 80s is that there were a lot fewer of these events. There was actually 8 years in a row with no. So typically these events happen 6 times a decade. There was actually 8 straight years with no sudden warming event, and that's actually the plot I showed with the temperature, with cold in our region, cold in Greenland and warm in Siberia was actually because of that, because there were 8 years in a row with none of these events. And other times we'll have, let's say, in one decade we'll have like 11 events. So there's, in which we're trying to understand why that happens.
I'm trying to understand what is the main difference between the different models. For example, the old model and this new one.
Yeah. So essentially, what exists currently in global climate enterprise is essentially there's about 20 to 30 modeling centers around the world that 20 to 30 countries in the world that invest in developing a global climate model, or global weather model. Essentially, you take all the Navier-Stokes equation of describing the fluid atmosphere and put it on a rotating sphere, and you take those equations, you run it on a model, you put it in a supercomputer, and you run it. And there's essentially about 20, 30 countries that have the infrastructure to do this. And they then both weather and climate. And then besides that, you also need to represent not just the physics equations, but also clouds and radiation and in the ocean and land surface and cryosphere. There's a whole bunch of different things that are less well represented or more difficult to represent on typical resolution. So a typical weather model will have a resolution of 10 kilometers by 10 kilometers. So anything that's on a scale smaller than 10 kilometers by 10 kilometers, you have to sort of parameterize or essentially guesstimate how they should function. And different modeling centers will have different assumptions on how to do that guesstimation. And the net effect is that you can have, let's say, some models are better than, I mean, you can then quantify skill, how well they do on weather timescales, and say, okay, this model is better than this model, and then you run it for climate, and you sort of take the 30 models you have and do the best you can with that. But in general, they will disagree, and part of what we do is make sense of this disagreement. Why do models disagree? And you can do a process level based understanding and also just a basic skill score, and hopefully they relate to each other, but not always.
אני אשאל את השאלה בעברית, אולי בתגובה תדבר קצת יותר לאט, אז אני אוכל גם להבין את התשובה. לפני 4 שנים, לא, זה נהדר. לפני 4 שנים הקמנו פה ועדה באקדמיה בראשותו של דן יקיר, לדון ולהמליץ המלצות בענייני אקלים. אני לא זוכר אם אתה קשור לוועדה או לא.
אז לא הייתי, כן, לא שיטה.
בכל אופן, ההמלצה הראשונה שלהם שיצאה בנייר עבודה, נדמה לי לפני 3.5 שנים כבר, הייתה להמליץ לממשלה לממן מחשב לחיזוי אקלימי, בגלל שהרזולוציות של המרחקים בארץ הן מאוד מאוד קטנות, ולכן אני לא זוכר את הפרטים, אבל המחשבים האירופאים והאמריקאים הם לא מספיק טובים כדי to account for ההבדל בין ירושלים למעלה אדומים או ים המלח. אז אתה יכול להגיד על זה משהו?
כן, אז כדי לעשות דאונסקיילינג, אז כן, אז רעיון, יש לנו מודלים עם רזולוציה של 10 עד, אם זה מזג אוויר, זה גג 10 קילומטר, אם זה מזג אקלים, זה... כן, ננסה. אז כן, אז השאלה לגבי רזולוציה, אז צריכים לעשות דאונסקיילינג. אז זאת אומרת, אז אם הרזולוציה של מודל מזג אוויר או מודל אקלימי הוא 10 או עד 100 קילומטר, ואם רוצים להבין מה יקרה בירושלים לעומת ים המלח לעומת תל אביב, אז צריכים רזולוציה של... זה יוצא בפועל 2-3 קילומטר. למשל, שמעת, כשהם מריצים מודל למזג האוויר, אז יש 2 מודלים, קוזמו ואייקון, שניהם הם מריצים ברזולוציה של 2 קילומטר. אז מה שצריכים לעשות זה לקחת את הפלט ממודל אקלימי עם רזולוציה של 70 או 100 קילומטר, ולעשות, להטמיע את ה-large scale בתוך מודל מזג אוויר בפועל, ברזולוציה של 2 עד 3 קילומטר, ועושים את זה, כאילו זה כבר התחיל, אז כבר היה קול קורא, היה גם בשנת וגם יש קבוצה ברשת העברית שאנחנו עושים את זה, שלוקחים את הפלט, והחלק יש יתרון וחסרון. היתרון הוא שאפשר להגיד משהו על ירושלים לעומת תל אביב, לעומת כאילו חיפה. החיסרון הוא שבפועל עושים את זה למודל אחד, וזה דורש כאילו, בפועל זה כאילו 10 מיליון, 20 מיליון דולר, רק מודל אחד. ואם רוצים, והבעיה שיש לנו 30 מודלים, ואי אפשר לעשות, אם ניתן לנו כאילו 200 מיליון דולר, אז נוכל לעשות את כל ה-30 מודלים, אבל בפועל צריכים לבחור רק מודל אחד או שניים, לעשות את התהליך הזה, ולא בהכרח אנחנו יודעים אם זה משקף את כל האי-ודאות שיש. אז, אבל לפחות מודל אחד או שניים, שאנחנו כן עושים את זה, זה כבר התחיל, זה אנחנו כן עושים, ומקווה שבשנים הבאות יהיה תוצאות.